Okay, so thank you for the introduction. So yes, my name is Massucci. I'm a PhD student from the University of Lauer, and I've been working with Fabien Lauer and Marion Gilson on today's presentation, which is entitled Regularized Switch System Identification, a Statistical Learning Perspective. So the aim of this talk is to show that we can use AI and system identification techniques in order to produce new solutions for estimating hybrid systems. So here's the outline. So in the first time, I will present a specific context of hybrid system identification, and so the problem of hybrid system identification. So we'll focus on switch systems, which are systems composed of multiple modes that will arbitrarily switch from a mode to another according to a switching sequence. Then I will present a method that estimates the number of modes of a switch systems using structural risk minimization, which is a model selection method coming from statistical learning theory. And then I will present what could be the benefits of regularization for the analysis of such models. So first, here we have a CISO arbitrarily switched ARX system. So as I just stated, it's a system composed of multiple modes. And so we will switch from a mode to another according to the switching sequence. So here you have the function FQI that denotes a submodel. And so this submodel will be active or not according to QI, the switching sequence that will active or not a mode at each time I. The problem of such systems, of the identification of such systems is, so given a data set and a set of possible submodels, we want to estimate the number of submodels, C, the corresponding submodels, Fj, and the switching sequence. So over the last 20 years, the literature proposed a lot of methods to identify such models. So here I distinguish two types of methods. So there are methods for a fixed number of modes C. So here we need to fix a hyperparameters which corresponds to the number of modes of the switch system in order to identify the model. And there are other types, other methods where we need to fix now a threshold in order to estimate C. So we need to fix a threshold on the prediction error in order to estimate the number of modes C. So the challenge of this talk is to show that we can use statistical learning techniques to estimate the number of modes. So to do so, we will use the structural risk minimization. It's a model selection method from statistical learning, where we will derive statistical guarantees on the prediction error in order to select the model with the best guarantees. So in other words, it remains to say that we want to choose the number of modes C that minimizes an upper bound on the prediction error. So before giving more details about the method itself, I need to put some basics of learning theory. So here's the setting. We work with a pair of random variables, x, y, of unknown distribution, and with the corresponding training set. And we work for a set F of possible submodels, of possible models. And according to that, we obtain a typical form of distribution-free risk bounds. So we say that with probability at least 1 minus delta, and for all the possible submodels, we will upper bound the risk in red here by the sum of the empirical form of the risk plus a confidence interval. So as you can see, so the risk in red is defined as the expectation of a loss function. And so in regression, the form of this loss function will be the square loss. For the empirical risk, it's the empirical form of a red one. And for the confidence interval, this parameter depends on a measure of the complexity of the model. So there exists common complexity measures such as VC dimension and Rademacher complexity. These measures are computed using statistical learning theory under the IID assumption on the samples. So IID for independent and identically distributed samples. And they depend on the loss class of function defined as follows. So here the bound that we will derive are made about according to Rademacher complexity decomposition. So we will use Rademacher complexity. Here you have a definition of the empirical Rademacher complexity with here sigma I corresponds to the Rademacher variables, which are random variables uniformly distributed in -1 and +1. So it is a random noise that we associate to the loss to a loss function. So it means that this Rademacher complexity measures the ability of the model output to fit with so these Rademacher variables. And so we use this complexity in order to develop this confidence interval in blue here. So using this Rademacher complexity, I present here a theorem where we develop this confidence interval according to the Rademacher complexity decomposition. So now that we stated a general form of a bound using Rademacher complexity, we can illustrate the use of such bounds in some examples. So first, in linear regression, so we consider the corresponding model class of linear regression. Here we see that we have the parameter RW that is here to control the complexity of our model class. We will use the following loss function, so which is the prediction error of degree P of our system. And so using a contraction argument, we will express so the Rademacher complexity of L such that of the Rademacher complexity of F. And then we can use a standard computation of this Rademacher complexity in order to develop this Rademacher complexity term of F. And we can see that in this Rademacher complexity, in this empirical Rademacher complexity, we find back so this term RW that controls the complexity of the model class. We can do the same in switching linear regression. So we consider the same model class because it's still linear models. And the main differences is located in the loss function, because here you can see this term. We will minimize the prediction error for each point for all the possible submodels. So I can illustrate it with the following figure. Here we have a system with two modes, and so we will associate the points to the nearest modes at each time. So using this loss function and using other Rademacher complexity calculus in the same manner as I did before for the classic linear regression. As we are in switching linear regression, a novel parameter appears, which is the number of modes in the expression of the empirical Rademacher complexity of L such that of F. And then, so using all these materials I just presented, so for the linear regression and the switching linear regression, we obtained two final prediction error bounds. So in the case of a square loss for P is equal to 2, we obtain these two bounds. So where we find back here the risk, the empirical risk, plus the confidence interval, which is developed. And the same for the switching linear regression. At this point, we obtained two bounds that are valid in only in the static case. The objective is to obtain a bound in the dynamical for dynamical systems. The major problem is that in learning theory, we are under this IID assumption that does not hold for dynamical systems. So to overcome this issue, the proposed solution is the following. We will assume that the data are beta mixing. Using this property, it means that the dependence between two data points will decrease with a time interval between them. So, for example, if we take here the first point of my data set and the 6th point of my data set, the dependency between these 2 points will be weaker than the dependency between 2 consecutive points of this data set. So, using this mixing property, we'll apply the independent block methods from U. It does consist in divide the original n data set with an n dependent data into 2 mu blocks, composed each blocks of A points. And by next only keeping the odd blocks, we'll see that the dependency between the odd blocks weakens with the size of the blocks. So at first we have an n data point at n data dependent sample, and now we have a mu blocks less dependent sample or sequence. So doing so, our data are less dependent, and we can apply bounds as I just present, similar to what I presented before. So indeed, now we can derive bounds using mu blocks instead of n data points. There is a novel parameter that appears in the confidence interval. It is the mixing coefficient beta of A that holds the degree of the mixing process, the mixing sequence. So now we can distinguish 2 types of bounds. So we have a bound in the IID case where the confidence interval depends on the n data points, and you have another bound in the non-IID case, and so here the confidence interval depends on the mu blocks that I just introduced before and the mixing coefficient beta of A. So now that we have a bound that holds for the non-IID case, we just have to adapt it to the previous result I just presented in the switching regression case using Rademacher complexity. And so we can obtain a confidence interval similar to this case and adapted with the C parameters that represent the number of modes of the system, of the switching system. So using this bound, we can we are able to estimate the number of modes of switching of a switch system using what I just introduced before, the structural risk minimization principle. What we do is, so according to our data set and by fixing a maximum number of modes C, we'll run a generic algorithm to estimate a model with C modes. And for each mode, the number of modes that we will test, we will compute the error bound that I just noted here as J of C. And at the end, we will select the best number of modes by choosing the one that minimize the criterion I just introduced here, so which represent the bound. So I illustrated this method into a numerical experiment. So the case we study here is a switched ARX system with 3 modes of order 2. We processed 100,000 points under Gaussian noise with a signal-to-noise ratio equal to 10 dB. And so here at the middle of the slide, you have at the top the empirical risk, and at the bottom you have a confidence interval. As you can see, along with the number of modes, so as the number of modes is increasing, the empirical risk is decreasing. It is because the more we have modes, the less we do mistakes, and it's reflected by the confidence interval that measures the complexity of our model. And indeed, according as the number of modes is increasing, the model tends to be more and more complex. And so when we have too much modes, we tend to overlearn. So finally, by doing the sum of these two terms, we obtain the bound, so the criteria J of C. And we can see that a minimum is achieved at C equal to 3, which corresponds to the true number of modes of the system we are studying. So an evaluation of this method of over 100 trials and with a color noise shows promising results in a paper that has been submitted in CDC last year. And we also confronted this method to other ones, so to algebraic methods, in a paper which is to be appear in CC of this year. So one more question we had to answer is what could be the benefits of regularization? So first, regularization is a standard technique to control model complexity while learning from data by minimizing the trade-off. So here we minimize the trade-off between the error term and the regularization term. And according to the parameter lambda here, we will give more or less importance to the regularization term. So as you can see, the error term is defined as the sum of the loss class. And here we have a novel regularization term that corresponds to the norm of the complexity of all the submodels that we have in the system. So this measure of complexity is a more fine-grained measure because using it, we consider the number of modes, but also the complexity of each submodels. So using this, now we are controlling the complexity with this term and not with the latter term I presented before anymore. So using now this type of model class and using the regularization, we can obtain a new type of error bounds. So a bound including the regularization. And so the parameter has changed. We don't have only C anymore here in the bound, but we have a parameter alpha depending on C and Q. So Q that characterize the norm and C the number of modes. So we can see that we can distinguish 3 cases. So when we have Q equal to infinity, it corresponds to the previous case, so where we considered only independent submodels. And so we had the dependency on C. So it means that the confidence interval is linear depending on C. So if we double the value of C, the complexity of our system will be doubled, and so will be less relevant. And we can see that modifying this Q, so choosing Q equal to 2 or Q equal to 1 will be a bit better, because we will move to a square root of C or log of C. So the case Q equal to 2 is the more classic case. It remains to do the square of the sum of all the complexity of the submodels. And for Q is equal to 1, it is the sparse case. So we tend to, with a L1 norm, to a sparse complexity, and then this allows us to have a log of C, which is a lot better than the C that you had at first. With such a log of C in comparison of just C, we won't explode in complexity by increasing the number of nodes. So I illustrated it with another numerical experiment. So here we are in the case Q is equal to 2, with switch IRX systems of 6 modes of order 2. So we processed 300,000 data points under Gaussian noise with a signal-to-noise ratio of 30 dB. And we can see that a minimum is achieved at C equal to 6, which corresponds to the true number of nodes. So you can find more information and more about the different or type of norm in the paper that will be submitted in the ADHS of this year. So now, as a conclusion, in this presentation, we presented new error bounds for switch system in the non-ID case. And we used them in order to propose a new model selection method in order to estimate the number of modes. And we proposed a refined analysis with a regularized model. There are still open issues because for the moment, we are not able to estimate the mixing coefficient beta of A I introduced, which is induced by the mixing property, make the hypothesis to make the non-ID bound. So this parameter is not necessary for our model selection method, but in order to fully compute the bound, we need to know how to compute this parameter. And then we would like to tighten the bounds in order to make the method more efficient with less data. So I thank you for your attention, and I will be pleased to answer to your question.
Thank you very much, Louis. Very, very nice presentation. We still have plenty of time for questions, so the floor is open for questions. Any question?
Maybe I can ask a question, but it's more, I'm not a specialist in hybrid system identification, but yeah, Louis was a participant of the Spring School, and Laurent Bacot has presented different methods to determine the number of systems and to identify the parameters. And Louis, could you explain why I should use your method more than the one of Laurent, or what are the differences, and in which case you should use this method instead of the more usual methods?
Okay, I could have a couple of different answers. First, as you can see, for the moment, our methods works for a large number of modes. So there exist numerous methods that works for for less points. As I presented before in the first part, we wanted our method to algebraic methods. So that works for 100 of points and or a couple of thousand of points. The difference could be in the fact that we can run this experiment for as many as number of modes that we want. This algorithm works, so it's not algorithm dependent. We can apply this method with any algorithm we want. So any identification algorithm we want. And it is not dependent of the type of noise or the
so
type.
You mean that you would run your algorithm in the beginning to determine the number of nodes, and then based on that information, you may use other methods depending on for the identification of the different nodes. Okay, well, thank you.
Louis, sorry to interrupt you, but maybe you have the big scheme where you have compared several methods, and it can help the explanation.
So yes, for example, we compared for CCID of this year, we compared our method to two algebraic methods. So the algebraic method from Vidal and the other from Jose. The one is in the noiseless case and the other in the noisy case. So what we pointed out is that some methods are effective for large data sets and others for small data sets. And the type of noise and the level of noise also influence the choice of the method. So you can see that our methods work for a large number of modes with any type of noise and under high noise and under any type of level or noise. And so it
Okay, thank you. Any other question?
I also have a question for Louis. It's Sergio. Hello?
Yeah, go ahead.
Hello, Louis. First of all, thank you for your presentation. I'm not also very familiar with hybrid systems, but I just have one simple question. You made the hypothesis that the structure of the models are the same. So does your method still work if the NA and NB changes in the different models? I don't know if my question is clear.
Yes, there is no problem about that. We don't make any hypothesis on the structure of a model or so on. So yes, that will work if the order changes.
Okay, so for example, if for model 1, NA and NB are 2, and for model 2, NA and NB are different values, your algorithm still works with no problem.
Yes.
It's just a random question, curiosity. I'm not trying to to trap you or something like that. It's just a curiosity.
Yes, so effectively it should work.
Okay, all right. Thank you.
Thank you. Any other question?
Can I ask or make a comment?
Of course, Christian.
Okay, thank you very much. First of all, Louis, thank you very much for your very interesting talk. I mean, it's a quite interesting use of statistical learning theory for hybrid identification. I just wanted to make a comment regarding the analysis that you did regarding, I mean, the use of mixing. I have a little bit of experience on statistical learning theory, but not so much on mixing. However, from what I understand, the idea of mixing basically is to decouple, right, this kind of independence, right? Now, decouple the dependence between the samples, right? In order to sort of, yeah, exactly. The thing is, from what I understand, in doing so, you lose a little bit. I mean, the bounds become looser. And sometimes the bounds behave in a kind of counterintuitive way. For example, mixing bounds, from what I understand, tend to suggest that the slower the process is, the more data you need. So the bounds become worse, basically, as the process becomes slower, because the samples become more dependent, right? So, it seems well that if you, for example, do some calculations just based on asymptotic variance, you realize that sometimes that's not what you would expect in practice. For example, if you have just an autoregressive process of order 1, and you estimate the variance of the only parameter that the process has, that variance sort of is of the order 1 minus a squared, let's say. And if the process is slow, that means a is closer to 1, the asymptotic variance tends to 0. But mixing bounds tend to sort of suggest that the variance actually increases the slower the process is. So in the last few years, I think in machine learning, there have been some kind of alternative approaches to mixing. There are even papers called learning without mixing. I think there is one by Ben Recht and others that basically try to develop kind of alternative approaches to get sort of tighter bounds in a sense. I don't know if you have explored some of those approaches, perhaps.
Not yet, not yet.
It's just a suggestion. I mean, that you might be interested in exploring.
Christian, I guess what you're talking about when performing this mixing is that you lose some dynamics each time you perform mixing. Does it come from the fact that you lose some dynamics?
It's just that, I mean, you require the blocks, I mean, to be kind of, I mean, to get samples that are more far away from each other, right? In order so that they are more and more independent. So that sort of suggests that the size of these blocks has to be larger, in a sense, to achieve sort of the same bound that you would obtain in the IID case. This is as far as I understand. But sometimes when the process is slower, estimating some of these parameters, the process can be actually actually easier, not more difficult. This is something I read just in that paper. I think I mentioned Learning Without Mixing, where basically in the introduction they discuss these kind of issues. Yeah.
Okay, thank you, Christian. Any other question? Okay, so thank you again. Thank you very much, Luis. Very, very clear presentation.
Thank you, Louis.
We'll move to the last presentation now. And the last presentation is going to be done by Vincent Musso.
Yes. Yes. I will share my screen. Okay. Do you hear me?
We hear you. We do see your screen, but I see myself on your screen.
Okay, I will share my presentation. Okay. Okay, do you see my presentation?
Not yet. Xavier,